Hello and welcome to a video on analyzing graphs of factored polynomial functions. So we're basically going to look at functions like this one that you see already factored, and we're going to analyze it according to, it looks like a lot of steps, but really what we're going to do is we're going to look at the end behavior model by looking at the first term. So we're going to collapse this to see the first term, get x and y intercepts, and then look at the graph on a calculator to kind of see where the local max and mins are and then make a sketch from that. That's essentially what we're doing. We'll get the domain and range out of there and see where the function's increasing and decreasing as well. All right, so let's start by just taking a look at a function and seeing what we can pull out of it very quickly. So first thing is I see that it's already factored, and I see that there's 1, 2, 3, 4 factors here. So from each factor, I'm going to be able to pull out some zeros. So the first factor, negative 4x squared equals 0, that's true whenever x equals 0. And because the 4x squared has an exponent of 2, we know that that has a multiplicity of 2, and therefore at that x-intercept of 0, it's going to touch, because whenever there's an even x-intercept, it touches. So it touches versus crossing through the x-axis. All right, the next factor, x minus 2, has a 0 when x equals 2. And that x-intercept also has an even multiplicity. This time it's 4. But what's important is that it's even. It doesn't matter how high the even number is, which means this one also touches. Okay, the next factor is x plus 3. And I should say here always equals 0 because we're always finding the zeros. X plus 3 equals 0 when x equals negative 3. And that one has a multiplicity of 3, which is an odd multiplicity, which means it crosses the axis. Okay, and then the last intercept, or the last factor here is x plus 4, which gives us an intercept when that is equal to 0, an intercept of x equals negative 4. That has a multiplicity of 1. There's an implied 1 there, so the multiplicity of 1, and that means that that one also crosses. So we have already a start of some basic information here from just looking at that. And it's very helpful that it's already in factored form to be able to get that information easily. Now the next thing that we want to look at is going to be, we can get the y-intercept. Since we've got the x-intercept, let's go ahead and get the y-intercept by finding f of 0 for the y-intercept. And that would be negative 4 times 0 squared times, and it doesn't matter because once you multiply by 0, it's 0. So the y-intercept is 0. So the y-intercept is 0. All right, now let's go ahead and take a look at what we can get from the first term. So this is where we collapse the function, and when I collapse the function, what I mean is whatever is being added or subtracted, I'm going to get rid of it. And by doing that, I'm looking at just the first term, the highest degree power function for this whole function. So I'm going to be looking at y equals, and this is going to be the power function, negative 4x squared. There's nothing to collapse there because there's nothing being added or subtracted. This just turns into x to the 4th. This will turn into x to the 3rd. And this will just turn into x. And again, this is not, I'm not saying that this is like the function. I'm just saying this is the lead term. If you were to multiply this whole thing out, this would give you the power function that would be the first term in your long polynomial and multiplying the whole thing out. And that would be y equals negative 4x to the 2 plus 4 is 6 plus 3 is 9 plus 1 is 10. So we know that the end behavior is just like an even power function that's reflected vertically because it's negative. So we know the end behavior. We don't know, we're not talking about the stuff here where everything close to the origin. We're just saying that somewhere on the outside it's going to go down in both directions. Okay, so there's our end behavior model. All right, so let's look at the directions here and see what we've done so far with the steps. We've determined the end behavior. We found the y-intercept, we've looked at the zeros and their multiplicity, and now we're ready to take a look on the graphing calculator and see what this looks like. You can use Desmos, graphing calculator, or the app on Chrome. Okay, so after entering the equation in the calculator, the first thing we would try would be Zoom 6. And with Zoom 6, we get something that at least it makes sense for what we're looking for, but it's not very clear what's going on, and it's going to take a little bit of trial and error to get to the right window that actually makes sense here. But what we do see is we see this over here. So we see that there's an intercept at, this is -4, and we see from -4, that being the farthest left intercept, from there it goes down. And we also see that there looks to maybe be an intercept here at 2, although it's a little bit hard to tell with this window. And at 2 we expect an intercept that touches, and then from there it's going down. So this is pretty much the entire activity of the function near the origin. Pretty much everything is in this range between -4 and 4. But we're just going to set that window from -5 to 5. And after a lot of playing around, which I encourage you guys to do this because it's not always easy, I'm going to change the window from -5 to 5, because that, I know, that's not an educated guess. That's really like a very much firm knowledge based on where we found the intercepts. But I ended up, after playing with it for a while, see that if I make this 12,000, and I make this 8,000, and I make this an increment of 1,000, just because it makes it easier to see what's going on. With that, this is the graph that I get. Alright, now this is much more clear, because now we can see that it crosses at x equals -4, and it goes down. It crosses again at x equals -3, which I already expected, and it crosses there. So it's going to cross at that point, come back up, touch at 0, and then touch again at x equals 2. So everything that we expected we have. You can see the end behavior model here, that at -4x to the 10th does show up. By the way, the higher the degree here, the harder it is usually to find the window, so it will take a little bit of searching sometimes. All right, we want to sketch this window. So I'm now going to just make a sketch of this. So remember, when you're looking at something on your calculator, use a rectangle to show that. This goes from -5 to 5. On the x-axis, just a little bit above the middle. And this, like I said, and here's the window, goes from -12,000 down here to 8,000 up here. And then the graph looks like it's got just something like this. You're not going to make it perfect, but you're just going to do the best you can do. We don't really want arrows in there, we just want to go to the bottom of the screen. Okay, so that's pretty much it. Now we're able to find all of these important points. In fact, we already know that this point right here is -4, because we've got, we really don't need the calculator for a minute just to sketch the x-intercepts. We know that at -4 there's an x-intercept, so that's the -4. We know there's one at -2, so that's this one. We know there's one at -3, that's this one. We know there's one at 0 that touches right here, so there's that one. We don't have to write that. And we know that there's one at 2. So right there is the 2. Now we can, it looks like that one at 2 might actually be a local max, but we need to go through the process of finding all these other local maxes and mins so we can see where this function is increasing and decreasing. So we're going to go ahead and find this local max. So I'm going to go second calc and then go to the max, go to the end of it. So I have to go all the way over to the left of that local max. Okay, that's good. Hit enter, go to the right of that local max, hit enter, and hit enter one more time. And it looks like we've got a local max at about -3.8 and then 6693.4. So this is -3.8. and then 6693.4. All right, there's our local max. Now we've got a local min down here, so let's go ahead and find that. Now I know that the screen is a little bit annoying here, but we may as well, sometimes it's just better to just go with it and just, as long as you know you're to the left of it, and we did see the min was there, so, and I know I'm to the left of it right now. I drew it right here, so I know what's happening here. Hit enter when I'm to the left. Go to the right, so when it's on its way back up, which I can see it now, so that's going to be good enough. Alright, so I've got a minimum here at negative 1.5 and then negative 11,407.6. So this right there is negative 1.5 and then negative 11,407.6. Okay, we're just rounding everything to the nearest 10. Now again, it looks like 0 is a local max, but let's just make sure. So we'll go second calc max and just go to the left of the 0, which we're already in that area. Enter. Go to the right of that 0. Enter. And one more time, and we have that exponent of negative 8 tells us these are definitely 0. So this is the point 0, 0. Let's get the local min right next to it. So second calc, min, enter, left, to the right, and we've got a local min right here. Let's put an arrow right here at 0.83 and then negative 1401.3. So this is at 0.83 and negative 1401.3. And then one more, just check this local max, make sure that it is in fact the 0. So let's go to the local max, second calc max, go to the left of it, we're already there, go to the right of it, and we've got a local max at, whoa, exponent of negative 25, that's definitely 0, and that looks like it's 2. So there's 2, 0, there's a local max. And we already knew that it was 2, but now we know that it's 0. All right, so now we're looking at the function with all the details. We're ready to write. Let's kind of go through our checklist, see how we're doing with our analysis. So we've used the calculator to graph it. We've used the graph to find the turning points. We've sketched the graphing window and labeled all the intercepts and turning points. We just need to find the domain and range and where the function is increasing and decreasing. All right, so we've got the domain. Since it's a polynomial, the domain is all real numbers. Since we've got a local max here and that's our highest point, the range will go from negative infinity all the way up to this 6,693.4. So there's our local max, or our range. Would go from negative infinity up to 6,693.4. And let's talk about where this function is increasing and decreasing. So it's increasing from negative infinity to that local max. So from negative infinity up to negative 3.8. And we have to shift gears here because when we talk about range, we're talking about y values. When we talk about intervals where it's increasing or decreasing, we're talking about x values. It's increasing also from here, which is negative 1.5 to 0. It's increasing from here, which is 0.83 to 2. Okay, and then where is it decreasing? And that is from negative 3.8 to negative 1.5. And again from 0 to 2. And then again from 0 to 0.83, not to 2. Decreases to the local min, which is 0.83. 0.83. And then it decreases one last time from 2 to infinity. And there it is. That pretty much ends the analysis. We've got domain, range, we've got a nice graph of the function, we've got all the local max and mins graphed on the function and clearly labeled. We've got an end behavior model here, which looks like that as far as the end behavior. And we've got all the intercepts shown here and whether those intercepts are touching or crossing the x-axis, which is consistent, of course, with the graph. Okay, I hope you found this helpful.